Hello, my name is Scott Sheeter. I'm a principal engineer at Slipstream. The topic of this video is daylighting controls. It is part of the ESTCP Advanced Lighting Controls Technology Transfer video series. Daylighting control is a lighting control strategy that automatically reduces electric light output in response to available daylight. Note that daylight controls may be referred to using a variety of different names, including photo control, daylight harvesting, and daylight responsive controls. But for the purposes of this video, we'll simply use daylighting control. I'll begin by describing daylighting controls and why we want them, followed by some discussion on the energy savings opportunity. I'll describe the factors beyond controls that impact daylighting and where UFCs and energy codes require automatic daylighting controls. I'll conclude with a few best practices for capturing lighting control design intent. You might wonder why controls that automatically reduce electric lighting in response to daylight is desirable. There are several reasons, with the most obvious being energy savings. Sustainable lighting design practices encourage the integration of daylighting into spaces where we live and work. Lighting affects how we feel, impacting things like mood and our ability to concentrate. We increase energy savings by optimizing automatic control of electric lighting, which also reduces the risk of creating glary, overlit spaces by continuously adjusting electric lights to maintain proper illumination. It was previously more challenging and expensive to control and dim fluorescent lighting, but with the increasing adoption of LED lighting, many of these challenges have been mitigated. Perhaps you find yourself wondering what kind of savings can we expect to realize. According to a meta-analysis conducted by Lawrence Berkeley National Lab, and published by the Illuminating Engineering Society in 2012. The average lighting energy savings from daylighting controls is 28%. Let's explore how daylighting controls yield those savings. Here we see a plot of an existing lighting system's power draw over a typical day in blue. Note that this system does not have daylighting controls. In the morning, the lights come on to their full power and remain there throughout the day before being shut off at night. When the system is retrofit to incorporate daylighting controls, the lights still come on to full in the morning. However, as the sun rises and the daylight present in the space increases, the lighting power is reduced. As the sun sets in the afternoon, the lighting power increases back to full power before being shut off for the night. The orange shaded area on the plot represents the energy savings that result from automatic daylighting controls. In the previous video, we discussed an advanced lighting control strategy called task tuning. You might wonder how these two lighting control strategies interact when combined. This plot illustrates the combined energy savings over an ideal day. Task tuning savings are indicated by blue shading, and automatic daylighting control savings are indicated by orange shading. The solid red line plots the lighting system's power draw over a typical day, when both task tuning and automatic daylighting controls have been implemented. After task tuning, the lights come on to their tuned power, just as for the system without photo control. As the daylight increases, the system needs to provide less electric light, resulting in energy savings on top of that realized by the photo control. The savings from task tuning is actually the same for if the system didn't have photo control. In fact, the only time that the energy savings is different from the system without photo control is when the amount of daylight is sufficiently high that the lights are dimmed to near or at their minimum. We will touch on their savings interactivity later. However, it should be noted that since there is less lighting energy to save after tuning, the savings component for daylighting controls is less. Beyond the controls themselves, there are other factors that can affect daylighting within a building and the savings potential for an application. Having some awareness of these factors can help identify the best applications for the addition of automatic daylighting controls. Daylighting design itself is an expansive topic that cannot be addressed in this short video. However, I will briefly identify the most significant of these factors. Architectural properties such as the shape of a building's footprint and orientation are important. Buildings with a longer east-west axis that maximizes north and south facades is ideal, as daylight is easier to control through glazing facing these directions. Another factor is window-to-wall ratio, which is the percentage of glazing in comparison to the percentage of wall area. 35% window area with higher window head heights is ideal. There's a trade-off in that as window area increases, the amount of heat loss or gain through the window via conduction or direct solar heat also increases. This balance impacts both the amount of useful daylight and occupant thermal comfort. The properties of the glazing itself, such as visible transmittance, also have an impact. A visible transmittance of 50% or greater lets in light while preserving views of the outdoors. Lastly, the presence of external shading can reduce unwanted or glary daylight without the need to close interior blinds. Interior design elements that impact daylighting include factors such as the color and reflectance of surface finishes, the height of cubicle partitions, and the type of blinds installed. As once they are lowered, they are often left closed for long periods of time. Lighter finishes with higher reflectances, lower partition heights, and automated blinds or non-opaque blinds can positively contribute to daylighting of interior spaces. And the electric lighting design has an impact on the savings potential associated with automatic daylight controls. The layout of the luminaires themselves in relation to windows, the density of the installed electric lighting, and the typical hours of operation of a building are all factors to be considered. Buildings with higher lighting power densities and longer hours of operation are likely to yield more savings, particularly if those hours of operation are still during periods when the sun is up. I mentioned previously that increasing adoption of LED lighting mitigated cost and complexity associated with dimming electric lighting. This is due to the inherent dimmability of the technology. The plot you see here illustrates the rapid adoption of LEDs within the new and replacement interior lighting market. According to DOE estimates, LEDs made up only 15% of installed indoor lighting in 2016, but by 2018 that percentage had doubled to 30%, and trends suggest that value is accelerating as we look at 2020 and beyond. As the percentage of commercial spaces illuminated by LEDs continues to grow, so does the opportunity to implement advanced lighting controls that capitalize on the inherent dimmability of LEDs. The indoor lighting applications with the lowest proportion of installed LED lighting, and therefore the greatest opportunity for remaining lighting and lighting control energy savings, are applications where linear fixtures, low bay and high bay fixtures are installed. These are all fixture types found in abundance on typical military installations, meaning an abundance of opportunity to capture energy savings through adoption of automatic daylight controls, as these types of fixtures are replaced by LEDs. So more specifically, where do energy codes and UFCs require daylighting controls? Automatic daylight controls are required in both primary and secondary side-lit zones, as well as in top-lit daylighting zones. Automatic refers to the lighting control system's ability to adjust electric light levels in response to available daylight without occupant intervention. Note that this figure is in section view, which is another way of saying from the side. In side-lit applications, the depth of the primary daylight zone is equal to the height from the floor to the top of the window, also known as the window head height. The secondary daylight zone is equal to twice the height from the floor to the window head height. ASHRAE 90.1 includes illustrations like this one and others to provide clarity in less straightforward applications. Note that a minimum amount of lighting power must be present in these zones in order for the daylighting control requirements to take effect. Similarly, ASHRAE 90.1 provides illustrations like the one shown here and others for top-lit daylighting zones, resulting from both skylights and roof monitors. As opposed to the previous figure, this figure is in plan view, which is another way of saying that it's from above. The top-lit daylighting zone is defined as the area 0.7 times the ceiling height away from the skylight. Note that if there are any significant vertical obstructions, the area that they block from receiving daylight is not included in the daylighting zone. Automatic daylight controls are implemented by locating at least one photosensor in a daylight zone, which collects information required by the lighting control system to determine if electric lighting should be increased, decreased, or even turned off to maintain target light levels within the daylight zone. The photosensor is often located on the ceiling or a lighting fixture. Its field of vision is the working plane receiving daylight. A group of electric light fixtures located within a daylight zone can be programmed to operate uniformly across the single lighting control zone. This zone-based lighting control approach saves energy, as intended, but does leave some savings on the table. An alternative approach is to install fixtures with luminaire level lighting controls, or sensors integrated into each fixture that independently respond to daylight. In a luminaire level lighting control application, fixtures nearest the windows dim more than fixtures further from the windows. Fixtures dim more on a sunny day than on a cloudy day, and fixtures with an obstruction view dim less than those without an obstructed view. This new market-ready technology makes compliance with energy codes and UFCs simpler and are easily adjusted in the case of either negative occupant feedback or a change in how a space is utilized. In addition to overall simplification, luminaire level lighting controls also provide an opportunity for deeper savings because of the dense sensing array characteristic of a technology that incorporates a sensor within each luminaire in a space. We'll discuss in more detail in another video in this series a Department of Defense demonstration that retrofit existing fluorescent lighting with new LED lighting that included these type of controls. When the addition of automatic daylight controls will be a part of a lighting retrofit, lighting practitioners should ensure controls and their intended operation are captured as part of the documentation provided to a contractor, such that a project scope is clearly defined. This example control matrix is one way to capture the design intent for automatic daylighting controls, as well as other advanced lighting control strategies. Unfortunately, this type of documentation is not standard practice for many retrofits, so must be requested by a facility manager. Important elements that need to be captured when implementing automatic daylight controls, and shown here in bold text, are whether daylighting control should be enabled or not in a space, as well as the target illuminance or light level required for the space. Note that daylighting controls are likely not required in spaces with no daylighting present, such as interior spaces. This brings us to the conclusion of the video. More information on this topic is available on several websites. Browse to these organizations' web pages and simply search daylighting to find a plethora of resources. The Design Lights Consortium also maintains a qualified product list that includes LED products with luminaire level lighting controls and daylighting controls. Thank you for watching.